Well, I hail from the United States, Chicago. Lived there for about 35 years and became interested in, well, I've been interested in mechanical things since I can remember, trying to build things out of Meccano, Tinker Toys, whatever it was, whatever there was a machine, I could open it up and look inside. I was always interested in how do things work. And that went on to motor cars, degree, and then a finance degree and an MBA. And so I don't use a degree except probably in this. I am in real estate, so that is what I do. This is how I spend. And skeleton clocks that you can see the mechanical insides of are what I'm interested in. So I don't own a single cased clock other than a grandfather clock in my living room. And that's the one that I use to tell time. I remember years ago, my mother visited me, and she would look around and see all of these wonderful skeleton clocks, and she'd say, well, you know, Mark, this is all very pretty, but you really can't tell the time. And that's often the case on a skeleton clock. I said, oh, Mom, that's not the point. On this one, though, you actually can see the time. We've decided to use enamel dialing, and some of the dialing is still coming. But basically, the way this all started was really by accident. There was a cover of Horological Journal. I think it was, Derek, what was...
Just behind you, on the title.
Right. So it was October of 2003, my. That's a long time ago. I saw this clock, and I saw the escapement on it, and I happen to be a person who likes complicated escapements, remontoire in particular. I think I have 30 clocks with remontoire. So I wanted to buy this, and in the article here there was no way to get a hold of Derek. So a friend of mine who's a little more worldly than me on Europe and so forth finally got a hold of Derek. We held a conversation, and I asked to buy this clock, and Derek said, well, we can sell this to you, but what I would like to do is to get started in making what I guess in Europe is called bespoke, custom clocks. So my friend Olivier also wanted to have one made, and he got first crack at it, and Derek made for him, which I'm sure you've seen, a Breguet-style double pendulum clock, similar to this, but a wall hanger. And while that was being done, and I got to actually experience and see the kind of work that Derek can do, I began designing this. What was to be a much simpler design, I decided to throw everything that I could financially do and imagine into it, because much to probably Derek's chagrin at this point in time, I knew I'd never get a shot at finding a man who could do what I wanted to have done. And I can tell you, I had briefly run the simpler design by a few other American clockmakers, and they just laughed. They said, no way, I'm going to do this. I couldn't even quote it, and by the way, I'm not going to spend the kind of time to do it. So, as that clock was made, and this, I began to imagine what I wanted done, and it was a very, very loose imagination. I have to tell you that 99% of what you're seeing here is not my contribution. This is all Derek's work. He takes what I imagine and makes it 3 times better. We have a relationship where when we speak to each other, it's like we're on the same wavelength, and then we talk, and then things get better and better and better. And the fact that something like this can be created over a long distance with my only seeing this once before, 3 years or 4 years earlier, is an amazing testament to Derek's perseverance and integrity, that he stuck with this project for so long. It has not been an easy deal for him. For me, it's no problem for me. So basically, getting down to the clock itself. I see Derek has provided my pointer. I've had a little bit of an advantage over you in that I was able to come here a couple of days earlier, thank goodness, and see this, and we discussed it a little bit first. The first thing that you're going to notice on this is his work. How he manages to make all of these parts in such a delicate manner. Now, how many of you here have actually been following this on the website? Okay, all right. Then you know that all of this is made by hand on a jeweler's fret saw. It's not computer-aided design and manufacture. We're not sticking any of these parts in a mill and out it comes. The other thing that's amazing about Derek's work is that when you see wheels like these escape wheels, or even these anti-friction wheels, they look like that to the naked eye straight out of the jeweler's saw. So the finishing that's needed is, I mean, obviously it's necessary, but what he does by hand out of the saw, you can almost put into the machine and it operates. So what we have here is, depending on how you want to count, anywhere between 35 to 50 complications. And if I knew I was going to be having to recite each and every complication, I would have brought my notes. But to run them through very quickly, and Derek, feel free to add whatever you want. First, we have obviously mean solar time on this dial. We also have the equation of time, which is read off through the differential method rather than through a sector dial. So in other words, this hand here, which gives you the equation of time, will either be in front of or behind the minute hand by that plus or minus 15 minutes or so. On the very same dial cluster is also our sidereal time, which is read off by these two counter-rotating dials, hours and minutes. Now, to the best of my knowledge, I do not know of another clock that's been made that you can read all three off of the same dial with the same set of hands. Now, if you go to my website, there is a Margette's that was made that has 3 separate dials on one white dial that does that, but not done in this fashion. Next, we have up here in this dial cluster the calendar. Now, as you will see, as you can see, nothing is ordinary in this. We don't just have a perpetual calendar. Who wants a perpetual calendar? That's just, everybody's got one. What we want is a perpetual calendar that's good for 1,000 years. Now, how is that done? Well, every 4 years you have to add in your leap year into February. However, every 100 years you have to make an exception to that rule and not add that in. But then every 400 years you have to then reverse that and do it over again. And you have to do that because man's calendar does not follow the heavens. Eventually, if you don't make some fine-tuned changes, you will find that your seasons begin to drift. Then there is, in 1,000 years, you have to make another exception. We thought that that might be a bridge too far. Don't think I didn't ask for it. There are other things I asked for, but I didn't get. But that's all right, I got 99% of it. Now, the other thing that this calendar has, which others have done, but not many, is we have a digital readout for the years. And you'll see if you look closely that it is not a regular cylindrical odometer, but are actually have facets for each year, so that it reads out as a nice flat piece of digits. And that is another example of where we try to make this different and better than what most other clockmakers would do. Now, if you look closely when you have a chance, this here is what's called the perpetual calendar module. That module is what actually does the remembering of the exceptions and so forth to keep this perpetual for that number of years. Now, this also is the only perpetual calendar that I know of that is fully functional in both forward and reverse. So if you reverse this, let's say for 300 years, it will subtract all of the knowledge of the exceptions. And then you can move it forward another 300 years and it will be right. And then you can move it forward another 300 years and it will be right. Now, you're going to find out later when you start seeing how this is demonstrated why that's very important, because this calendar is used as a way of knowing where all the other celestial functions, what they are doing and when. So for example, the Ori, which you don't have up here yet, if you want to know where is Venus going to be in relation to Jupiter or Saturn or whatever in 25 years from now, you simply crank this forward until this is 25 years ahead, and it'll tell you exactly where everything will be. Right, that's true. The other thing that we can do with this calendar, in combination with this Tellurian, is that we can predict for the next 400 years plus and behind exactly where and when a solar or lunar eclipse will occur anywhere on the face of the Earth. And if you go to my website, there's a section there where Derek very well demonstrates how that's done. And you will also then be able to, once the planisphere is installed, you will be able to know where all the stars are at the latitude. This is set for the latitude of Chicago. I don't know why, but you know, why pick a city like Chicago? And know exactly when you look up in the sky where the stars are. Over here, we have a dial set that's not yet complete, and that will give you, again, at the latitude of Chicago where the sun is rising, when it rises and sets, as well as a rudimentary rising and setting of the moon. Anyone who has actually studied how the moon operates to reproduce that in a mechanical fashion is devilishly difficult. But we are approaching, you know, a rough approximation of how that's done, rather than just a simple rolling moon that goes around like what you see in a regular grandfather clock. Now, on top of that, we have also another 2 trains. We have 4 trains, one for the time, one for what I call the celestial train. That's the train that operates all the complications. And then again, another 2 trains for a quarter and hour strike. Now, the celestial train is kept isolated from the rest of the time train through a remontoire. Now, as I mentioned briefly before, remontoire is a particular interest of mine. So there are several types of remontoire that's commonly used in horology. One is, you're probably all familiar with, is the Harrison-style spring remontoire, which generally operates right on the escapement. There is the train remontoire, which in most of its forms is a type of differential. And then there is the Robin remontoir, which is a chain remontoir that you may be familiar with in French clocks. When I was designing this, I thought that it would be very necessary to have a remontoir because I like those, but it would be better to have every single doggone remontoir I could think of. So, we have here a spring remontoir, a Robin remontoir, and not just a gravity-driven remontoir, but two of them coupled together through a differential. That remontoir, the one that's coupled through the differential, is based upon Henry Baptiste Wagner's design, and if you look him up, you will see his remontoir, or you just go to my website. I have a whole section on remontoir. In my opinion, is visually the most pleasing type of remontoir that's been made. So if I can get one that's the most pleasing that I find to be, it's better to have two. Now, the other thing I wanted to do, and again, the three things that I wanted to accomplish with this clock, the three principles were size. In other words, it had to be bigger than a normal clock, but not too big that you couldn't put it in a domestic environment. So I didn't want it to be like Jens Olsen's clock in Denmark, where it's from like that wall to here. That has more complications, but it's from that wall to here. So I couldn't do anything with that. The other is that it had to have complexity. And the third, which is where this really will outshine probably anything else that's been made, is movement. Now, you all have been here long enough to see that there is something going on in this thing all the time. My goal with this machine, and I think we've accomplished it, is that I want it to grab you by the throat when you walk in the room and not let go. I want the person who walks into the room to go, and I don't want a word uttered from their mouth for 5 minutes while they're still looking at it and wondering what's going on. Why is this happening? You'll notice, if you look at it long enough, there's a teeny little fly fan on the inside, which you don't notice very often, but it's there. And it cycles at odd times, not always in a consistent manner as these two do. And that's done on purpose because the human mind recognizes patterns very quickly. So if you have a fly fan, and this fly fan, by the way, it operates the remontoir for the celestial train, on average once a minute, but not always once a minute. And that's fine, because the celestial train moves very slowly, and as long as on average it's released every minute, it will do just fine. But if it is exactly every minute, then it's not as interesting. And everything we did here, when we talked, when Derek and I would approach a problem and say, how do we make this subsystem? It always was with a focus of, how do we make this as visually stunning and as entertaining to the eye as possible. If you go to my website, you will see what I collect is nothing but eye candy. It doesn't have to be famous, it doesn't have to be old, but it has to look really cool. So, in keeping with that, I went with what I thought would be visually the most interesting escapement that I could find, and that is Harrison's escapement. Why? Because a regular clock outside of the pendulum and the escapement is pretty much a static device. But Harrison gives me two pendulums. Two is always better than one. Also, with a dual remontoir that is coupled through a differential, that allows me to have two escape wheels. And of course, why have two escape wheels moving in the same direction? Let's make them in the opposite direction, and let's curve the spokes so that you get a kaleidoscopic effect when you're looking at it. Again, we're doing this all for visual appeal. Then, as we started making the escapement, and I think, Derek, this was, I think by accident on our part, going with the bird design. I don't think we really went into that on purpose. It sort of got there. But as we were developing the escapement, it started to look a little bit like a bird with the comb and the beaks. And then I said, well, this is not a bad idea. Let's add some feathers. And it looked great. So then we said, okay, we are going to use this bird motif throughout. And when you think about it, what you see here is a classical base, a forest that's populated by vines and trees. If you look very carefully at all of the pillars, they're all like tree branches and vines, and at the end of the vines are the big red jewels. That's the fruit of the forest. And what good is a forest without animals? So we populate it with some animals. And then above that forest is the firmament, which will be represented by the Ori, the planets and the moon. The other thing that this machine does is it gives you a view of our cosmos from 3 different magnitudes. The first is the planisphere, which is not attached. But that is what man sees from where he stands. He looks up at the heavens, he sees the stars. The next is represented by the Tellurian. That is our kind of inner area. And in addition to a normal Tellurian, because we don't want anything normal in this, we also add Venus and Mercury. And then the third magnitude is at the top, where you're having the entire solar system seen. So you can, by demonstrating this, you can make all 3 of these complications, as well as the sun and the moon rising and setting. That also is on the first order. That all can be demonstrated simultaneously. So you can see at any time where everything is from every position that you could be in, from either on the Earth, from near Earth, or from very far away. Now, in the demonstration mode, we have a little transmission here. That transmission has 2 different speeds. Slow for being able to demonstrate the functions of the Tellurian, sunrise, moonrise, and set, the sidereal time, as well as the calendar. There's also a fast forward function which is used to demonstrate this alone, which would be the Ori, because of course you have Saturn and Jupiter, which move extraordinarily slowly. And if we had it all in regular mode, you wouldn't be able to see them move very fast. And I want to see things move. Next, we have these 4 indicators here, which are actually just duration indicators showing you how many days are left on the clock. That is just in case your neck has surgery and you can't look any lower and see where the weights are. So if you can only look this far, you have those. This is an example of, well, why did he do that? Because I could. That's basically what that is. Next, you have this little area here, which is your setting dial for the equation of time cam. Take a close look at that cam when you have a chance. You will see that, yes, it's a kidney cam, just like any other kidney cam for an equation of time, but it is made to look like the rays of a sun. Now, what better way to depict a time of the position of the sun than with a cam that looks like the sun? So it's another little whimsy that we add into the machine. Next, we have our strike train. Now, it's really nice to have a strike train that goes ding dong, and it's nice to have a strike train that will also tell you what the quarters are as well as the hours. But it's better to have one that will also give you grand and pettit sonoring. Now, anyone who has worked on this type of a mechanism, usually a clock that does both of those is designed to just do that. You just pull repeat and that's what you get. But this one also will operate as a regular quarter striker in combination with that ability. That is not an easy thing to accomplish because in a normal clock, when you get near the time for striking the hour or the quarter, it has to set itself up. Well, if it's set itself up, and then you pull the repeat and you want to know what it is a minute prior and it's already set up, it won't work. This is Derek's genius. He figured that out. That's got nothing to do with me. But it is a complicated little devilish device which is located right up here, and it is an auxiliary power source to not only power the repeat function, but there are several other mechanisms in here that helps to disable the setup and allow it to properly repeat, and then put that setup back again so that when it's time for the clock to function as a normal clock, it will. Now, the other thing I wanted to have happen, and this is something that is reflected in one of the tower clocks that I own, is on the quarter, it will give you a bim bam, as a normal quarter would. And then at the end of that, whether it's 1, 2, or 3, the hour will strike once. Now, why that is, I don't know, but the tower clock was built that way, and I decided to incorporate that into this because it gives you more fly fan movement, okay? If you're just doing a regular bim bam on the quarters, then all you're seeing every quarter is this moving, and this doesn't do anything until the hour. This way I get this doing it every 15 minutes, and I get to have that do it every 15 minutes. Now, when this thing strikes, and I don't know, is it set to strike now?
This is a classic demonstration. It is for some.
It's not striking.
Not striking.
Well,
we can just have a quick look and see why it hasn't struck. I've been watching the time all the time. You want to go out? Okay. I think we have the. It should strike for us there.
now this is set to grand sonnery, so it's going to strike obviously the hours after each one. If it were set normally, it would strike only once, and then it would strike the hours on the 12 o'clock. Now you'll see these fly fans are very special. If any of you are familiar with American design by a man named Charles Fasselt, I don't know if any of you know that name, but that is an American watch and clock maker who he didn't have a large output, but what he made was extraordinarily beautiful and commands incredible prices. He would be like the George Daniels of American stuff. He had a fly fan on a couple of his tower clocks that had this epicyclical type of gearing. A friend of mine in the U.S. owns probably half a dozen of his things. And so I called him up one day and I said, you know, Don, I'm going to steal from you. I'm taking this. And of course he said, sure, go. You know, obviously it wasn't his to give, but as a joke I said, you know, I like this and I'm gonna take this. we modified the design, or Derek modified the design, to where it's even better and more interesting to look at than what Mr. Charles Fassel had done. There are several things that we've borrowed from other makers, their designs. Harrison is obviously one, Charles Fasselt is another, Mr. Wagner for his remontoir is another. There were several different types of designs that I saw bits and pieces of that are in my collection that I wanted to incorporate into this.
Martin Burgess winding barrel?
Right, Martin Burgess's winding barrels, that's of course all Derek's idea. And by the way, going to the winding barrels, you can see here that we do not have a whole lot of drop. We've got about 24 inches of drop. Now again, for people who make clocks and understand physics, you are looking at a tremendous amount of mobiles here. There's all kinds of things going on. That all takes energy, takes power. Remontoir or power hungry. All of these things take power. There's only two ways to provide it. Lots of weight that's highly, what am I trying to say, multiplied by pulleys, or a large amount of drop. What we did here is we have 24 inches of drop. What is it, Derek, 3 inches a day?
That's right.
So 3 inches a day on a one compound pulley. So we're not compounding these things 3 or 4 times, just once. We can get a full day on a 3 inch of drop. That is a very efficient design, considering all of the things that you're seeing happening here. Every single thing that catches your eye takes power, every last one.
Mr. Frank, sorry if I can interrupt. Somebody asked me just now, who was discussing.
Yeah, ask any questions and interrupt me anytime. Because I could go on, when somebody comes to visit my collection, I tell them, it's all day, fellas. It's an all-day affair. Okay, so go ahead.
We just did a quick rough calculation of how many revolutions we get on those top 2 sets of fly fans in a week. It's 1.8 million revolutions.
Wow.
Is that for both or each?
All 4 flies
Okay,
taking roughly 10 revolutions.
I got it.
Yeah.
Okay.
So if you divide it by 4, and it's
Got it.
600,000
Per week.
per. Yeah. Well, it's a lot.
That's a
But
lot.
that comes out of our 2-foot drop.
Right. Now, what you're seeing here also, what I wanted to convey was, with the visuality of this, was to add a little bit of color. So instead of seeing only a brass clock, we chose to go with enamel dials to give a little bit of contrast and color to it. In addition to that, we went with jewels for our bearings, and then for our roller bearings, we use these little plastic red end caps. That also acts as a dust cover. Now, when you get a chance, if you go around the back of the clock and you look at the screws that are associated with the pendulums, those are the right color. Those are the electric blue that I'm looking for. And Derek and I went through quite a few iterations of different steels and different methods and so forth, and quenching and oil or not oil or whatever, to get to that exact color that I was looking for. So if you go around the back, you'll see that. That's not this color here, and it's not this one here. It's the ones that are in the back, which give you that color. The other thing, as far as the screws were concerned, in horology, basically you use a cheesehead screw. It's, as you know, that's just a flat top, black polish is the traditional way of doing it. The problem with that is that only looks good if the angle of incidence of the light is coming in, hitting that, and getting to your eye. If you move just a little bit, it's black. I didn't want that. So we domed all of the screws so that when you look around and you're walking, it's always following you like the eye of a painting. so that it adds a little bit more of an interest to the clock. You'll see on the columns up here, we use a Doric column, get a little bit of a bulge to it, give a little bit more interest. If you look carefully here in this perpetual calendar, we have what, how many parts now, Derek? 550, I think?
I've forgotten one.
Yeah, it's about 550 just in this one subsystem alone. The total number of parts, I think,
We're heading somewhere between 4,000 and 5,000 parts.
actually I thought it was more, but that's,
Well, it may be.
is that all of the parts, screws, everything?
I'm not sure.
I thought we were closer to about 7. We don't hit 7, I want a discount. Forward or?
Clockwise as per the international time dial. We
Okay,
didn't
right.
We didn't mention the international time dial.
Got it. The international time dial is here and has currently 4 cities on it. What do we got? We've got Moscow, London, Jesus, Chicago's on there again. And Sydney. Sydney, what's Sydney doing out here? Okay, so, as you move this, you can see all of the celestial functions, and again, with the Orion top, that would also be moving. So, everything is going, your Earth, your Venus, Mercury, and now it's ringing on cue. So now you're seeing everything moving. If you look at the 2 concentric inner dials here, you see them rotating counterclockwise, and that is allowing you to read to the minute what the sidereal time is at any given point. Now you'll also notice that the calendar is stepping at the same time. So you're seeing, here comes Friday, here comes Saturday, the 21st, now comes the 22nd, and so on.
Today's the 24th.
Well, we're going in fast forward. But since you want it to be the 24th, we can reverse it also. And it will all go backwards. Now Tuesday, now Monday, and there you are. And again, you can use this calendar to then visually look at everything else and say, well, where will all these things be, and what will all these things look like in the next 2, 3, 4 years? And you can do it up to how many years you want. Now, in practical terms, as you can see, you'd have to do a lot of cranking if you wanted to go 300 years into the future. There is a fast mode, which allows you to do things quicker. I'm not sure how that works, Derek.
Not complete yet.
It's not complete. Okay, I'm out of there. I don't have to do that.
If we pull that further up there, sorry, it comes at another stage there. If you turn that section there,
It'll drive the Ori faster.
at high speed.
Right. This to move, as you can see, everything's moving very quickly now. But even so, if you want to go 3, 4, 5 years, you've got a ways to go.
Best to use the internet then.
Right, best to use that. Right. You know, it's really to show you how these things really work and how they all interact with each other.
Tell me, the way science is going, it looks as though there's another solar system out there somewhere. Are we going to build on top of that?
Show me that solar system.
Another complication.
Derek's going.
I know there's probably lots of questions, but I wonder if we could hear from Derek and tell us a little bit about the production or the process. I know a lot of people don't appreciate that you actually made a full-scale model in timber. Is that still here, or is that?
It's up on the mezzanine with cobwebs. What happened was, we had, and this is the whole relationship between Mr. Frank and myself, is that we talk. And finally, first of all, Mr. Frank gave us the requirements, and I said, yes, I can do it. And he said, are you sure? And I said, I think I can. And he said, well, you know, how do I know? I want to see some plans. So we drew paper plans, it ended up about a 6 or 7 layer plan, which we then went on film so you could superimpose it, and it looked quite interesting when you shrunk it down, but it didn't work. But anyway, we had these plans, and then the size discussion came up, and I said to Mr. Frank, what do we need to do is we need to make you a mock-up so you can see what you are getting. And what I did was I cut out, without teeth, but cut out each wheel on its pitch circle diameter and fitted everything in. So we had a 3-dimensional check on the plans, but also a very reasonable visual indication of what Mr. Frank was going to get. I then knocked it flat, put it in a box, and we sent it to Chicago. And Mr. Frank reassembled it there, and I believe you took it to a show.
Yes, a couple of shows.
And a lot of people thought it was a real clock. But it was more like a film prop. It gave you the size and the shape and the colour and the configuration.
But it was very good. I mean, down to the spokes, which I wasn't expecting. I thought the wheels would just be solid discs, and just to give me how it would bulk out. But no, it was really quite visually stunning.
I also sent some photos to Mr. Martin Burgess, who at that stage was just down the road from us in Chelmsford, where we were living, and got the usual demonstrative reaction from him, saying, you know, how is this possible? Harrison took, 10 years to build a clock, and here you've done one in 3 weeks. And then I had explained that actually he's looking at cardboard and paper. But the design process that established all our major arbor positions, the overall placing of most parts, and also our initial gear ratios. Once you start making it, most of it's just back of the envelope stuff. So we have I think it's about a 6-inch high. After a while I started keeping it, just for in case. So we have about a 6-inch pack of sketches and scratches and scribbles, where most of the design work takes place. Some of the more complex parts, like the Tellurian, I draw out in fair detail, where you've got 6 axles inside each other, and tubes and bearings, and I can't imagine that much. I can handle about a
And some we made mock-ups. We actually made plastic mock-ups of the dual remontoire, and the escapement all the way to the pendulums. That was one of the early ones. A mock-up of the planisphere, and a mock-up of this perpetual mechanism here, to see that it would actually work.
The complex ones we actually make maybe 4 times oversized, but we actually make a little working model in Perspex. It's rough, but it works, and that gives you lets you actually play with it, and that brings hopefully some of the bugs out.
I think the other amazing thing of how Derek built this is that it was not something that you sat down and you made plans and said, here it is, now we build it. This is all built as we went along. And when you look at how complex this is and how these pieces have to fit together and how there's really no real estate left in here to make any kind of movement or mistake, things that require advanced planning, and I pointed this out to you, I don't know, a couple of years ago, Derek, when you planted this piece here, which was the arbor for the transmission. That was thought of what, 6, 7 years ago.
Yeah.
But that was a critical location
Yeah.
for other pieces that later came along that we had not even drawn out or made any kind of a design diagram for. But in Derek's head, he already has this thing, maybe not down to every single wheel, obviously, but enough that in the entire decade that we've been working together, there has never once been a major catastrophe where we painted ourselves into a corner and said, oh my gosh, we've just lost 6 months of work because this can't work. Because there's a conflict in an area of a part that now, for instance, these pendulums. If you look at these pendulums and you look at these diagonal bracings and then you look at how much stuff is in here, that's a very difficult thing to plan out. But that was planned out. Wasn't planned out right away on paper, but it was planned out.
Perhaps we could put it in another way, is that as Mr. Frank uses the expression real estate, we have plots. Like you'll notice here we have this hollow section here that looks empty. If I can put in the mock-up, which is also not exact, but when you put the orrery inside here, it fills that gap up. So I have a disc that's level with this area, that the escapement doesn't come above, that horizontal cross arbor doesn't come above. I'm just clearing here, just the front and the back when you put the dial in. That is all reserved for the orrery. So that's where the orrery is going to go. Now, what happens is when I get to that point, we stretch everything to use up the last millimetre. So I could have given myself a ½ an inch spare. But what we're trying to do is to make it look as complicated as possible. Now that's a proper strike. So once we've got the real estate left, when we build the building, we go right up to the boundaries to make it look more complex than it actually is. So when, for instance, like on the thresholds here, you'll notice the tip of the threshold just misses the strike arbors, I mean the winding arbors. That's stretched to just miss it. It could have been smaller. I mean, I can make it that size if you wanted to. But what we're trying to do is to fill out everything to give you the maximum effect. Same like when you're transferring motion across here, I'll pull these wheels out all as big as possible to make it look impressive, let's say. These wheels on the Tellurian, I've expanded. I mean, that arbor and the gear train there could have been tiny. We pulled that right out to this level to try and help counterbalance the weight, but also to fill it out visually. So while it looks, you know, absolutely crammed, actually we've just stretched it until we touch the boundaries.
So what Derek is saying is that this is really as simple as a cuckoo clock?
Yeah.
It's just all your imagination. That's all it is.
It's got a few less wires than the cuckoo clock.
I'm sure there are lots of questions out there, but can I start with one? Is the clock still evolving? Like, are there possibility of still further?
There is ongoing conflict. Mr. Frank has ideas, and I'm running out of time.
I think there's not much more change to go.
No, I think everything is pretty much finalised.
Pretty much fine.
It's just got to come.
Great.